All right. So let's start. So today's class is probably slightly long, but hopefully exciting. Okay. So we have many topics to cover. Okay. All right. So couple of topics are quick recap and just need to be clear that those needs to be recapped well. Okay. So we'll go over AOA, AOD, right? And essentially revise you that there is a four-dimensional analysis happening here. Okay. Right. And then we'll kind of reduce it to 3D when your AOA and AOD are the same, right? And then we'll recap how AOD and velocity are intertwined. Okay. All right. And finally, right, we'll have a more intuitive way of understanding this overlap and interconnection, right? And probably that will also give you insight as to how to disambiguate it. Okay. Right. Then we'll study this kind of will help you also disambiguate this more importantly. Then we'll go over the hardware architectures, right? And I'll tell you about more interesting techniques, right? Which we probably haven't studied in this class, right? If you think about it, right? Most of our class has been trying to understand these things and connect them with FFTs. Okay, right? What we have learned is to how to do four-dimensional FFTs now. Okay, right? And two, we know that all FFTs, everything in the nature is FFT rather. Okay. Let me maybe quickly pull a few things which I want you to take from. Okay. The reason for pulling these things is just, yeah, so that you guys also remember it nicely. Okay. So let me point to the one. Let's start with this one here. Okay. If you look at this, right? Okay. Right. What we really have, right? Okay. Right. And then probably we can just quickly go over the model, right? The model is very simply following. Okay. What is the model? The model is we have multiple transmitters. Okay. Right. TX1 to TX4 or 3 or whatever, right? Okay. Right. And RX1 to RX4. Okay. Right. The problem is that essentially you get these reflections back, right? Okay. It was all good and fine, right, when we were using receivers because they were all operating at the same time. Okay. But turns out when you have these transmitters, right, either one of those transmitters is turned on, right, or the other one is turned out, right? And what it really results in is that, for example, you have four transmitters in this case. Okay. They are transmitting in four different time slots, right? This is transmitting for T or 0 to T rather. This is from T to 2T, right? And so on and so forth, right? And what we discussed the other day, right? And the problem comes when this object is not stationary. Okay. Right. So more specific to the point, right? Okay. Fij prime k tau, right? LT is essentially for each value of L, right? I is different, right? What is I for L? So let's say if L is 0, then I is equal to 1, right? Okay. How about L equals to 1? I is equal to 2. This is transmitting 2, right? Okay. How about L equals to 5? What happens if L is equal to 5, guys? Anyone?
I will go back to 1 because it's a modular operation
Uh,
based on the number of transmitters.
No. I will go back to once again.
2.
Huh?
It should be 2.
Yes, it will be 2. Okay. It's just a so I is as we discussed, right? Okay. L plus 1 mod 4. Okay. Make sense, Eric?
Yeah.
Okay. All right. So as we discussed, right, summing over LT requires you to take two things into account, right? One is your steering vector of omega, which is velocity is steering vector, right? And you need to also take into account the steering vector of transmitting antenna, right? With I minus one, right? When you're summing over L, okay, right? What happens if now if you take this and sum it over J prime? So by the way, this is MJ prime actually. M prime J prime, let's put it this way, right? It reminded me of Spider-Man. Any case, all right. Um, so looking at this iterative function, right? Okay. The next thing we can do is essentially we can sum M prime J prime, right? Okay, which is function of K tau nu and theta tx, right? With omega rx minus J prime minus 1, correct? Okay, and summed over J prime, right? What does this leads to? I think we defined this notation. Somebody wanna tell me what this notation looks like? I thought I had, yep, it's n, or rather n prime in this case. So this leads to n prime of theta tx comma theta rx comma rest of the variables, right? K tau and nu. Okay, everyone following this? This is summation of all the receivers on the angle of arrival side. Okay, right? So essentially what we know now is how n prime is function of k tau nu t, nu, let me write as nu, not t, right? Or you can just call it nu if not over c if you like. Okay, you can call it theta tx, right? Or sine theta tx, right? Okay, and theta rx. Okay, so this is like the four-dimensional transform output you have really. Okay, everyone following this?
Uh, can we go over like how we are uncoupling theta tx and
Yes, we will
velocity?
get to that. Yeah,
Okay.
thank you. Okay, now that you understand essentially how these things are right now the way they are, right? Okay, so now let me recap to the previous class, right? In the previous class, what happens, right? We assume that the transmitter and the receiver, right? Okay, are on one of the same platform. Okay, right? And the object from which they are reflecting back, right? Okay, it's far away. Okay, and for all technical purposes, right? Okay, signal transmitted to it or received from it, right? Both of them form theta tx equals to theta rx. Okay, okay. Now, Puneet, can you give me one idea on how now you can resolve this? The ambiguity function? Come on, folks. So what was the other notation we studied from the last class? Okay, let's go back and like take a review at it. Okay, so this was the notation we studied. Okay, right? That sine theta tx prime was a function of, this is your ambiguity, right? Everyone following this? This was your ambiguity function, right? Everyone agree with me here or following me here at least? Eric?
Yeah, I am following you.
So now that I said theta tx is equal to theta rx, right? Okay. How would you use this, right? You can only use your receivers, right? to get to theta rx first, okay? All the receivers. And from there, you know theta tx, and then you can substitute theta tx, right? And you already know this quantity because this is the quantity you're measuring, right? Then you can essentially calculate the velocity model of someone, right? Does this make sense? Puneet?
Yes, yes. So if TX transmitter and receiver are co-located, then we assume the
Yes.
AOD and AOA are equal. Then obviously, yeah, we can reduce the equations, number of
Right.
variables. Yeah.
Does that make sense, Renji?
Yeah.
So, but what is the problem with doing this? Why don't you tell me the problem as well with
Professor,
this?
I have a question.
Go ahead, go for it.
But in our system where we have multiple transmitters and multiple receivers, can we
Mhm.
assume that they're all co-located to have the same angle?
So that's again your system design, right? Let's say you're a radar designer for Navy, right? Okay. And hey, you say, I'm going to design in this way, right? Versus, hey, I'm going to design that such that they are not co-located, right? Okay. So it's a very much a design question, not a analysis question, right? So
Okay.
yes, you're correct, right? And we will come to that case now, Keshav, and we'll study that case as well. Okay. So, but I think at least we understand that when AOD and AODs are like transformed, right? What is the problem with this formulation? Can anyone point me the problem? Let's take an example, okay? Right? What if you have two receivers, right? And four transmitter, Keshav? What would happen for that matter?
Professor, what do you mean by what would happen?
Like, will this technique work really well? What we just described, right? Our process is first to find what? Theta of
TX.
Rx,
Oh, sorry, RX, and then we
because
find
it's all
TX.
receiving
Right,
at the one same time, right?
right.
Then
TX,
substitute it to be tx and then get to mu
the
naught,
velocity, yeah.
right? Okay. Now, why is this a problematic process in this specific case?
In this case, since you have less receivers than transmitters, the resolution that you're able to measure
Yes.
that data with is less, and so you're therefore limiting your guess on the TX as well.
Yep. Very much. Okay. That's the case. Okay. Everyone follows what Eric just said. Now, Eric, I think here's another question, right? Okay. You don't just have this information, right? Okay. About 2Rx, right? Okay. You have that information about 2Rx from transmitter 1, from transmitter 2, from transmitter 3, right? And from transmitter 4, right? Okay. So you can definitely average, right? Okay. But would average help you with your resolution? Look, I think I have 4 transmitter, right? Each one of them will give me receiver 1 and receiver 2, right? And I can get, with this respect to that, right? I can get angle of arrival theta, right? Again, I can do the same with transmitter 1. I will get theta rx prime, right? And then theta rx double prime, right? And theta rx triple prime, right? And theta rx quadruple prime, okay? Or triple prime in this case, or whatever, right? So this is transmitter 2, transmitter 3, right? Each one of them giving me this, right? Okay. But would that improve my resolution? What will this improve? I think today's class is more of a test for you as well as for me to see how well you have got these concepts. Keshav, go ahead, Eric. You unmuted. Why don't you go ahead?
Oh, I was going to say it doesn't help your resolution per se,
What will it help?
the accuracy.
Yep. Does that make sense, Keshav?
Yeah,
All right. Helena, makes sense, right? Averaging them, these four, right, helps your accuracy, okay? But does nothing for your resolution, okay? Right? If there is another reflection which is coming from this angle, right? Okay, it will be the same amount of closeness, right? And it will cause same amount of error in all four transmitters, okay? Right? Does this make sense now, the intuitiveness of this thing, this argument right now I just made? Okay, that's fair, right? Okay, so what can we do now? What can we do, guys? Puneet? Questions, Puneet? Sorry, if you're speaking, we cannot hear you right now. All right, any thoughts? How do we proceed from here, right? Okay. Going back to this equation, right? Okay. So clearly the way we are using the transmitters, right, is ineffective if it cannot improve our resolution, right? Okay. How can we use them now? Okay. So let's now, for now, assume that theta tx and theta rx are the same, but just that you don't have a lot of receive antennas. Okay. Right. So let's re-examine how and what we are trying to do. Any thoughts, any ideas? I don't see Puneet anymore. Is he still here? Yeah, I see now. Sorry, Puneet, you're saying something?
No, I got disconnected. So
Oh, I see. But any thoughts on how to go about solving this problem?
I didn't listen the last part. Yeah.
So the problem is following, right? I only have 2 receivers, 4 transmitters, right? Okay. And if I go by this process of theta rx, theta dx, and nu naught, right? I'm essentially going to get a very low accuracy because theta rx's accuracy or resolution is not that great, right? That would give me bad resolution on theta tx, right? And therefore a bad velocity estimation in this particular case, right? Okay.
Yes. Hmm.
So now how do we mitigate this problem? So what is the assumption? Theta tx equals to theta rx, right? Okay. Or the object is far away from radar. Okay. All right. And so we know that V naught T over what is that factor? Okay. 2 V naught T over STX, right? Okay. And when it multiplied by J2 pi, essentially has some good amount of phase going there. Okay. And it can cause problems, right? And it can cause problems because ideally, right, if the person was not moving, right, how would you solve this problem? First question is that. Let's start from there. Helena, ideas? Let's say person is stationary, right, and theta tx equals to theta rx, right? Okay. How would you improve on the resolution here? Keshav? Thoughts? Some random thoughts at least.
It will be based on the aperture of radar, right?
What does that mean?
Like that uh, total spacing between the TX1 to the RX and 2
So
here.
the answer to the question is rather like we'll leverage the transmitting antennas, right? At least that will give me more resolution than the 2 antennas I have, right? Okay. Does that make sense, Puneet? Keshav?
Professor, I couldn't follow you.
So my question is very
Right.
simple, right? Let's say the person is stationary, right? Okay. The problem comes when the person is moving, right? This term adds additional phase each time the next chirp comes in, right? Okay. Right. Correct. And
Yeah.
because of that, you can't estimate angle of arrival, right? Last time we discussed this, right? So we are trying to estimate sine theta tx, which is the actual angle of arrival, but we end up estimating sine theta prime tx. And this is because we have this additional factor of 2 nu naught t over stx. Okay, I see. You can't see my screen now. Sorry, my bad. Or it froze actually, not see my screen. You could see my screen, just didn't show the right thing. So basically, right, as we were discussing, right, the sine theta tx prime is essentially an outcome of having sine theta tx, but an additional term of 2 v naught t over t sine or transmitted distance of tx, right? Okay. Now, let's say if this person is stationary, right? Nu naught becomes 0, right? Okay. So sine tx, theta tx prime becomes the actual sine theta tx, right? In that case, right, what can you do, Keshav? You could potentially just leverage this, right? So you'll essentially get two receivers, right, for transmitter one. Transmitter two, right? It will cause some shift in these two receivers, right? Okay, one other receiver. So this will create a virtual antenna array, right? That virtual antenna array essentially lands up here, let's say. Okay. So you get one new information in space at least, if nothing else, right? Okay. Transmitter 3 does the same, right? Okay. And transmitter 4 does the same, right? Does everyone follow the virtual antenna concept here? Eric?
Yeah.
Keshav?
Oh, yeah.
Okay. So that way, at least you can improve the resolution, right? Okay. If object is not moving, right? Okay. TX can provide better resolution.
Professor, would this be accuracy or resolution?
Yes. Why don't you tell me now that question, right? When do you say something is accuracy and when do you say something is range?
So the resolution basically corresponds to how precise the estimation or how precise the prediction is.
Right.
Whereas accuracy corresponds to how often you are predicting the correct value.
Right. Okay. So now by increasing these antennas, right? Okay. Right. So if you kept on putting more antennas at the same spatial location, right? Okay. Then you would improve accuracy. But if you keep putting one new, for example, in this case, this virtual antenna array got another virtual antenna array, sorry, or virtual receiver, right? Which is at new location altogether, right? Okay. So overall, right, this is increasing your, what is this increasing, Keshav? Or Eric, Puneet, what is it increasing?
That one would be increasing the resolution, right?
It's increasing aperture and by corollary, it's increasing the resolution. Okay. Keshav, does it make sense?
Yeah.
Okay. Puneet, following me?
Yes.
So now tell me an interesting, or tell me one thought process, right? How to mitigate this problem? Now, anyone? So what happens when they're moving, right? Okay. This is your transmitter 1, 2, 3, 4, and back to 1. Okay. In this short period of time, right? What do you expect to happen?
The person would have moved and would not be in the same location.
That is true. That's correct, right? So this person, right, will start at V naught velocity here. It will be at V naught times 4t over c here, for example. Okay, correct? Make sense, Keshav? Now,
Yeah.
how would you compensate for velocity? More importantly, right, what would happen to angle of arrival from transmitter 1's here to here movement? Distance, initial distance will still remains d naught, right, for both of them, right? Okay. or you can say this is d naught plus v naught t over 4t over c, right? That's where this look is located, right? Okay, right? Is there some angle of arrival terms which is adding up here? So let's take this example a little bit more clearly, right? Like in this case, for example, there was a faraway object, right? Okay, let me redraw it. So come on, someone wanna give me a guess? Huh? So what really happens, right? Let's understand this from angle of arrival point of perspective, right? Okay. These are your receiver 1, 2, 4. Okay. Right. And this is your transmitter 4, or let's say 2 and 1. Okay. Now the problem is basically this one will make this, right? But this one, by the time it's here, it has moved, the object has moved by this, right? So it will essentially report some phase change on even receiver 1, right? Now, how do we measure angle of arrival, folks? Keshav? Go ahead.
We could compensate for that velocity term, right?
Now, first intuitively tell me, how do you calculate angle of arrival, right?
So AOA is the angle which that line subtends with the normal from the receiver.
Right. And how do you measure it in this case, for example? So when you measure this, right, okay, the way you measure angle of arrival, right, is by looking at relative phase change, correct?
Yeah.
Now, in contrast, now, okay, the issue is by the time it goes to transmitter 2, right, the first chirp was for transmitter 1, right, okay. The second time this chirp came around and it did its own cycle of transmitter 1, transmitter 2, transmitter 3, transmitter 4, right? Given that the object is far away, right? Okay, right? Okay, what happens is that with even v naught velocity, right, it wouldn't change your angle of arrival by much, right? Okay, so to be specific, right, next time when transmitter 1 hits, right, all these receivers, right, okay, what is the difference? The difference is that now the object could be at different location to begin with, right? Everyone follow me? Keshav, Eric, Puneet?
Yeah.
Yeah, I'm following.
Okay, so how will you now solve this problem? More specific to the point, right? Okay, transmitter 1, 2, 3, 4, 1, 2, 3, 4, right? Okay, what can you measure from this to this? 1, 2, 3, 4, and 5. Keshav?
We would know how far the object has moved.
Right. We will know how far the object has moved or what is the velocity of this object. Right. That will be solved by this. Does this make sense?
Right.
Eric?
Yeah. Yeah.
Okay.
And
Good.
Professor,
So now,
just to reiterate, this is because we know the range of the object, and then we know how long it takes to cycle through all of the chirps, and so that
right.
tells us the velocity.
True. True.
Okay.
But I think that assumption is quite true, by the way. Okay. In the sense that basically when you send these things out, right? Okay. Um, they essentially don't behave in the way you just proposed right now. Okay. Right. Okay. So more specific to the point, right? You can use chirp number 1 and 5 to figure out the velocity, right? It does not have any angle related components, right? Its angle of arrival won't change from 1 to 5, right? Everybody spot on and clear on this intuition? Puneet?
Yes, with the underlying assumption, yes, it makes sense.
Yes. So now what you really do is you make this assumption, right? And what will you get? You will get come on, folks.
We can find the velocity from this two one.
Yes.
First
So
and fifth
first
chirp.
we can find the velocity of these two, right? Okay. And then build a model and then compensate those velocities, right? From where, Keshav?
From the successive chirps.
From chirp number 2 to chirp number 5, right? You can
Right.
remove, or chirp number 4, right? You can remove the effect of,
The velocity terms.
right? You can basically normalize by velocity term, or you can have velocity 0 and to do bench test measurement. Okay, right? Does that make
Right.
sense?
Yeah.
Okay, all right. So this at least explains us how to go about decoupling velocity in AOA AOD model. Okay. To recap, right? Okay. The problem is that one equation decides the fate of two things. Okay. And that one equation is nothing else but this one, sine theta tx prime is equal to sine theta x plus what not this is. Okay. This term, right? So this term, right? Okay, needs to be used when you cannot figure out v naught or sine theta x, right? Okay. Everyone following me? Helena?
I'm following.
Great. Okay. All right. So the gist of the summary is basically, right? Okay. You can compensate for velocity, right? Number one, right? And average out. What should I average out?
I think the screen froze.
Yeah. Is the screen frozen?
Oh, I see. Sorry. Thank you for reminding me, guys. I'm going to turn off video, hopefully in the lux that it may be able to handle bandwidth or something like that. So now we can compute velocity, right? Okay. And compensate its effect, right? Okay. Does this help Puneet understand this process of how to disambiguate one or the other, right? Now, what are the problems with this? Go ahead, Puneet.
Like we this if velocity is big, like the observation period needs to be longer to actually get the correct estimation of for velocity.
Right. So if you only use few estimate, right? Okay. What is the resolution of V naught? Keshav? Come on. Keshav, thoughts, ideas?
I'm not sure.
Okay. Why don't you explain the thoughts or the overall question, how you understand it right now?
So we are able to estimate the value of V naught based on the readings from the first transmitter and the fifth transmitter.
Right.
And we are assuming that the angle doesn't change between them, and so that's why we are able to
Right. So
estimate.
that's the first assumption, right?
Right.
Okay. Let's
And
write it down. Next.
And so then now you're asking, your question was basically, given this velocity, given that we are able to estimate a velocity, how resolute is that value? Like
Right.
what's the resolution of that velocity
Right.
estimation?
Or more importantly, it's not about resolution, right? As we talked, right? It's about
It's
accuracy.
accuracy, right?
Right. Okay.
Yeah.
So it assumes that your V0 velocity also will not have values larger than 1 over, let's say number of transmitters are P, right? PT, correct? Everyone follow? It's the process when you compare 2 points is away by P of T, right? Even though if it is going to decide, let's say the outcome of one big war, right? Okay. At this point, this decides, and at this point, somebody else decides, right? So what happened really, right, is essentially this part of the component, right? Okay, flourished, right? Okay, in some ways. Okay, what does that lead to? That leads to that your velocity, right? Okay, cannot be slower. What is this, Keshav? Is this range or resolution?
Professor, I guess this is the factor of resolution, right?
This is no, not a factor of resolution. This is your factor of range, right? Sorry,
No,
no.
resolution, right?
Yes, you're correct. This should be resolution, right? Okay. No, wait. The overall process has been measured for P times T, right? Okay.
Right. So when you take it into the other domain,
Yes,
it comes down to resolution.
right. You're correct. Okay. So, sorry, my bad. Okay. So this essentially leads to your resolution. Okay. Right. But at the same time, what is the range?
1 over T.
No. See, the point is that you're getting 2 points. Each point is after 4T. Okay.
I see. Yeah.
Right.
Right.
So the range is total number of 4 NTs you consider, right? Okay. So that will be your range.
In this case, it would be P and T because you generalized it to P transmitters.
Right. Am I correct, guys? Keshav? Oh, sorry, not Keshav. Kunit?
Automatically also range is like lesser than resolution here, like so total observation time is becoming like 4 NT now.
Right.
Yeah, so
resolution should be 4. Let's call it PT for that matter, so that it's consistent.
this term should be resolution.
Yes.
The below one.
Right. And the range should be?
Simple space, which is 40 here.
Sorry, my bad. What am I doing? Sorry, guys. Yes, you're correct. Sorry, you're saying? In this case, it's because there are only 2 points we are considering the range and resolution are one and the same. Okay. It's your 2 frequency model, right? If you consider more of them, right, then you will get better range and resolution. Okay. The point I do want to make is following, right? Your factor will reduce by a factor of 4, right? Because you're getting 1 point after every 4 times T. Okay. So the maximum Doppler you could have measured now cannot be faster than 1 over 4T, for example. Okay. Right. Okay. Does it make sense, Keshav? Or 1 over capital PT. Okay. That's the max, Doppler max you can measure. Right.
Right.
Now, the minimum or the resolution is essentially depends upon the window you are taking into account, right? Right now, we are taking the same window account of P times T, right? Which is essentially like 2 points. That's why we are getting range and resolution to be similar, right? Okay. So this enables you, right? Okay. In estimating movement Okay. Does it make sense? Eric?
Yeah, that makes sense. I was just thinking that if we knew the user was moving radially, so we didn't have to think about angle possibly changing,
Mm-hmm.
could we take more than 1 point from the first transmitter to try and increase our resolution if we were willing to delay when we actually calculate the angle?
Yes. So that's essentially what we are doing when we put down these many points here, this one, right?
Mm-hmm.
Right? It's essentially waiting for these many points to appear to essentially perform this analysis, right?
Okay.
So now that we understand all these processes, right? Okay. Right. The problem is, right? Okay. We need to understand who is changing faster and who's changing slower. Okay. Right. Okay. Now, intuitively, it makes sense that velocity will change slow. Sorry, velocities changes, right? Okay. Will not cause significant. What would it not cause? Significant phase, right? Sorry, no significant phase. Sorry. What is it? Velocity changes will not cause significant. Physically speaking, okay, right?
And this goes back to our assumption.
Yes, very much. Okay, so the idea now, and then, so now the question really becomes, right? Okay, now you understand, right? So first what you can do is you can estimate velocity by doing 1, 5, 1, 9, and so on and so forth, right? And then you can subtract that velocity over time, right? Okay. So once you subtract that velocity over time, then you can use 1, 2, 3, 4, right? Okay. Plus you can use all the J primes to perform AOA analysis. Okay. Does this make sense?
Oh, yeah.
So let me now write down this as a block diagram. Okay. So I'm going to assume f k tau comma lt, right? First thing, and let's assume all fj prime, ij prime are available, or I is automatically function of L, right? Okay. But let's say you have these all these information, right? First thing you do is estimate velocity. Okay. And then once you estimate velocity, you compensate that velocity, right? Now, right, Keshav, now what do you have? You have I, or rather L, right? Okay. And what do you have here? J prime, correct?
Yeah.
Now you can use the summation on these, right? To estimate with high resolution. Okay. Does this make sense, folks? By the way, this is going to be super useful when you're trying to do your final assignment. Okay. Do you already see its usefulness? Who's here? How about Puneet?
Yes, because once we are able to estimate velocity, then a virtual RX array helps us in increasing the resolution for AOA.
Right. So let me ask a different question here, right? Okay. Why not do this other way around? First estimate AOA, right? Then do velocity.
It was because in this scenario, to calculate the AOA, we had to use our receiver values instead, and we had made the assumption that the receive resolution was lower than the transmit resolution, right?
Okay, yes. So basically the resolution at this point needs to improve. Only then you can use this approach. Okay, right? Okay. So by the way, right? Okay. Now here's the question, right? So first, if you started measuring angle of arrival, right? Okay. The velocity terms will cause your angle of arrival to be inaccurate. Okay. Right. And that inaccuracy, right? Once you compensate for that AOA, right, your velocity will kind of become zero, right? Okay. And the loop will stabilize, right? Okay. Roughly speaking, even if you tried correcting this again, right? Okay. It'll be really hard for it to correct, right? Okay. So on the contrary, right? Once you estimate velocity, right? Okay. And then you do AOA, right? Okay. And the output of this AOA, you can feed it back to the velocity model, right? Okay. And compensate those phases to see if the velocity checks out. Okay. If the velocity remains more or less the same, right? Okay. So that's one way to go about this iterative process, right? Okay. In last class, I was explaining one other interesting method actually. Okay. And this comes from your Fourier transforms. Okay. This one here required a lot more careful thinking, right? I think even though I draw this compensate velocity, right? This compensating velocity is going to make you think about your final assignment, sorry, midterms, right? One of the problem actually had compensation of velocity, right? And like, look how we did on that, right? I think it was kind of challenging to do this, right? So it's not trivial what we are trying to suggest here, okay? And it builds on a lot of your entire course, by the way, okay? Does it make sense how these things are non-trivial? Now let me try to give you one new intuition for how to think about this expression here, okay? So let's say if you did 4-dimensional transforms or 3-dimensional transform, depending upon how it is laid out the problem, okay? Sorry. Let's say this is the problem statement now, okay? So the problem statement is basically now what happens is your let's take an example, right? Let's say, so if you're doing now, let's say 3-dimensional transform for this matter, or 4-dimensional transform, either case, it doesn't matter actually, okay? So let's start with your M prime, right? Okay, K tau nu, right? F naught nu over C, right? Okay, and theta Tx, or rather Rx, both are one and the same in this case, let's say, okay? So now, when you plot this in 3-dimensional grid, okay, right? Okay, this gives you locus of all the solutions, correct? Right? All the points which have this or meet this feature, right, will have an answer, right? And will create strong energy, right? Does everyone follow what I mean by strong energy here? So let's take an example, right? When you do IFFT, right? Okay. Whenever K tau is equal to K tau 1, right? You essentially see a strong signal and a strong energy here, right? Okay. Now take this and extend it to 2-dimension, right? Okay. Take here another sine theta, right? Or take here Doppler, right? For that matter, F naught nu, okay? So what happens is that then this tau comma this nu, right? Where it actually has, you will get a very strong 2-dimensional sink, right? Okay, right? Everyone seeing this sink? Following this sink? Keshav? It's like
Yeah.
as if you pull the cloth from this point up in the air, right? Okay, and you see essentially that sink going out on both sides, okay, right? So now similarly, right? Okay, so what is our problem? Our problem is this F naught nu over C, right? Okay, gets confused with sine theta tx prime, okay? Because theta tx is the underlying, theta tx prime is what you estimate, okay? Right? So what would happen here is that at these points, right? Okay, and let me kind of draw this point here now, okay? This point here, okay? This will have high energy around this point, okay? More specific to the point, right? This value here, right, will be equal to, depending upon nu, right? Okay, this value will take different points, okay? Does this make sense? So just to explain this, right? The new value here, right? Okay, is something, but there is some other higher value, right? Which will lead to some other point here, and that will lead to some other theta here, okay? Everyone following this? Keshav
Yeah.
or Eric, Helena?
Yeah,
Yeah, I'm following.
Good. So essentially, Puneet, how about you? Puneet?
I'm still thinking, but no, I'm not clear. I'm thinking, processing is still.
Okay. All right. I think this is probably you can kind of even plot, right? Okay. And try it out. Okay. And probably your last assignment, for example, right? Okay. Or last lab, right? Probably should give you an opportunity where you can add some velocity and try this out, right? And what you will see is that as you decrease this velocity and as you increase this velocity from V naught here, okay, right? Okay. For all those points, right? Okay, your theta will go up and down based on that, okay, right? And ideally, assuming that there are like not a lot of reflections out there, right? Okay, this will become your like resolution. This ball sphere will become your resolution, right? And the center point of this ball most likely is your solution, right? Now you may ask a question, right? Hey, what happens if there are two paths, right, in same vicinity and same ball like radius, right? Then my friend, that is not a good solution, right? Then you're like essentially basically you're gone into worst case scenario where there is no right answer to that question, right? Because there are many answers to that question, okay, right? Because you are now violating resolution, right? Okay, these two balls overlapping with each other, right, will give you a larger ball and whose center is what you will think as a solution, but turns out there are two different solutions, okay, right? So just to draw this, right, there will be another kind of a sphere here, right? Okay, right? And because you're trying to say that the center is the right answer, right, in that case you will make up like this, right? Okay, so there is a trick to this as well, right? Okay, the way to think about this problem is that you look at the distribution, okay? So if it is a sphere, right, then there is only one solution, right? But if it looks like two spheres, then there are two solutions here potentially, okay? And this is probably where you can probably apply some deep learning or some kind of machine learning techniques to understand this better behavior, okay? Does that give you better intuition, folks? Yes, no, either one is fine, right? Before I move on to hardware architectures, I want you to kind of give a conveying sense on what, how, and how about you think about this one? Questions, Puneet? If you are speaking, I cannot hear you.
Yeah. So I do get with the change in velocity, obviously, uh, theta prime will change, tx prime.
Mhm.
But okay, but if we like have an estimate of angle of like this solution will be feasible only when we assume AOE and AOD are equal, right? Like
Yes.
then only it
And
helps.
even four-dimensional, you cannot plot maybe that four-dimensional thing, right? Okay.
Mm-hmm.
Still, this rule will hold.
Now, at that time, I'm thinking when we actually do the transform, like
Mhm. So transform will result in all the high energy points wherever
Yes.
this equation is satisfied. Okay. This
Yeah.
equation is loci of all the points. Okay, let me stop sharing because it has paused. Okay. Actually, that's a good way to think about it, right? It's a locus of all the points where the energy will be high. Okay, right? Everyone follows that?
But even though we are saying it's a 4D transformation, but effectively it's 3D only because
No, it's actually
angle of,
something different, right? It's
yeah,
more 1D, right? You have one
yes,
piece of information and you're trying to estimate two things out of it, right? Okay,
yes.
right? And that's really the core of the problem here.
Mm,
Make sense?
I'm not like entirely, I'm confused about this, but I will think about it. Like, it
That's
would
okay.
come back.
Why don't you think about it? And if you want, we'll be happy to set an appointment and discuss this further. Okay.
Sure,
So
sure.
with hardware architectures, right? My plan is to discuss few things, right? How does FMCW generation work? Okay. Right. Okay. How does conjugate multiplication happens? Okay. Takes place. Okay. Right. Okay. So far, we have been operating in the world of complex. By the way, the world is real, right? Okay. Real samples create images. Okay. Okay. I think if we cover these topics, I think this is already a good start. Okay. All right. Okay. So let me explain, right? FMCW generation, right? What is FMCW? FMCW is frequency increasing with time. Okay. So let's say this is your time, right? This is your frequency, right? It needs to start from F naught and go to F naught plus B. Okay. Right. Okay. And so the idea here really is doing following. Okay. So there is something called as voltage controlled oscillators. Okay. And what do? They essentially, if you feed them a ramp, okay, right? Everybody knows ramp signal, right? It's like a voltage which essentially like goes like this. Okay. Right. Okay. And as it says, like a voltage controlled oscillator, right? Its oscillation frequency changes, right? As the ramp's voltage increases, its frequency increases. Okay. Right. So that generates a chirp for you. Okay. Now there is an inadvertent problem, right? Okay. What is that problem, right? This here, what I'm drawing is something called as open loop voltage controlled oscillator. Okay. Now, what is the problem with the open loop voltage controlled oscillator, right? So what happens really is following. Okay. So if you have open loop, right? Okay. What it means is that there is no frequency stability. Okay. Right. And what I mean by that is that you apply same voltages two times to it. Okay. Right. Right. The output of VCO, right? Okay, might generate this frequency, and in the next time it might generate this frequency. Okay, note that there is some additional frequencies generated here and some like lower frequency is changed. Okay, so instead earlier you started from F naught and you went to F naught plus B here, right? In next step you go from F naught plus delta, and let's say if it goes to F naught plus B plus delta for now. Okay, right? Now what is the problem with this? Anyone? Keshav?
It will make your FMCW estimation really funky because what we're doing when we're doing the conjugate multiplication is we're looking at the frequency difference
So
with the received signal, and we want those to be consistent between chirps.
let's see, let's understand that part. Okay, right? So let's say if this is your frequency generation, right? Okay, so now first chirp came, this is what you transmitted, and this you got as received, right? Okay, you can still estimate this to be delta F, right? Okay, same thing goes here, right? Okay, you can still estimate this as delta F, right? Okay, this is your reflection, by the way. Okay, right? Does that make sense?
Yeah.
Sorry, my bad. So this is your reflection, let's say, okay? Both of these, right? So ideally you got your reflection to work, right? What is the problem then now? Keshav or Puneet, Elena? Again, this is out of kind of like, I'm not expecting you to answer this. Just take a guesses here, right? What will break in your equations? So will range break? First question. Let's start from range. Will you get accurate range? Okay. So let's understand how do you get accurate range first of all. Okay. Right. Anyone want to take a guess? Okay. What happens? What would happen to range estimation? So let's first understand the second component of the architecture. Okay. And that will probably help you answer this question. Okay. Second component of the architecture is essentially estimating this delta f, right? Okay. Now we have been doing conjugate multiply, but there does not exist something like conjugate. Well, there exists conjugate multiplies, but typical people, they are expensive, right? Okay. So let's say, for example, what you do is you generate x of t. Now, instead of exponent, it's a cosine. Okay. 2 pi f naught t plus k by 2 t square. Okay. Everyone following this, right? Now, there does not exist conjugate. If your chirp is like this, by the way, chirp is typically like this, okay, right? And what is the difference between this chirp versus our exponent, right? The difference between this and exponent, right? Okay. Can someone tell me the difference here?
There is an image.
So let's understand this. This is essentially has, let's draw. This starts from f naught, right? And minus f naught. And this goes to positive plus b, okay? Right? With increasing time, okay? Right? Let's just say that time is in this case here, okay? I'm just drawing the chirp inverted, but the point is that there is a symmetric travel in the cosine, right? But in the case of exponent, right, only this thing exists in the case of exponent, okay? Right? Does this make sense? This part, the other part does not exist in case of exponent, okay? Following, guys? Keshav?
I'm still trying to process this, Professor.
Why? Sorry, why don't you explain me what's the problem? So, you know, cosine is exponent of positive j 2 pi whatever, right? Plus exponent of negative j of
Minus
the
j,
same thing, right?
right,
Okay.
over 2.
And over 2, right? This is essentially what I'm doing here, right?
Oh,
I
okay,
took
I
the
see.
positive and negative and that gave you the cosine, right? Okay.
Okay, yeah,
But if you just had exponent, that was just the positive part here, correct?
got it.
Um, who else is here? Eric, make sense?
Yeah, that makes sense.
So now let's do, and again, in real world, right, there does not exist conjugate multiplier. Well, let me not make that statement. There exists in some complex way, but let's do following, right? What you do is you take xt minus tau, right? Okay, which is your reflected signal. Okay, this is your y of t. Okay, this is your received signal. Okay, right? You multiply this with x of t. Okay. Now, what is your x of t, by the way? Okay, x of t minus tau into x of t. Okay, all right, this is your y of t. Okay, everyone following? This is the signal I'm trying to write down. Okay, let's call it r of t, or so far we have been calling it h of t, right? Sorry, let's call it h of t. Okay, right? Okay, What is h of t? Now let's do it, right? Cosine of 2 pi f naught t minus tau plus k by 2 t minus tau square, right? Times cosine of 2 pi f naught t plus k by 2 t square. Okay. Now somebody wants me to help me with this cosine thing. What is cos A cos B? Sorry, go ahead. Someone said something. Hello.
Cos of A minus B plus cos of A plus B.
Cos A into cos B is cos of A plus B, right?
Difference plus cos of
Minus cos of A minus B. Sorry.
summation, professor.
Can you repeat? What are you saying?
It will be summation, right? Cos of A plus B plus cos of A minus B.
Is that correct? Cos A cos B? No, I think this is
Cos
probably
of
correct.
no cos of A plus B is
Cos A
cos
cos B plus
minus sin A sin B. Yeah.
Yeah, it's minus sin A sin B. So
yeah.
So when you
That's
subtract, you
fine.
are adding.
Sorry.
You are adding the sign terms here.
Oh, right.
No,
Sorry. My bad.
cos-
Yes, you're correct. Okay. Any case, right? This is probably not the most important point, but let's see now. This is your A and B, right? You add them up, right? Okay. Right. What will that lead to? A plus B cosine of A plus B will essentially lead to 4 pi f naught t minus tau, right? By 2. Okay. If you want to put this as in this here, all of it, right? This tau by 2 is just to balance out that 2 pi. Okay. Everyone with me on this? Plus um, k by 2 t minus tau square plus t square. Okay. Right. For all technical purposes, this is like another chirp of its own, right? Okay. Because it has some t square term in it, right? Okay. And some like all other kind of terms in it. Okay. Right.
Professor, would this have an amplitude of 2?
Huh?
Would
1
this
half.
be
It will be 1 half. Sorry, what do you mean by 2? Why 2?
so? Cos A plus B plus cos A minus B is gives you 2 times cosine A plus cosine A cosine B, right?
No, this
Yeah,
is how
yeah,
it
yeah.
works.
Okay, so okay.
Yeah.
Yeah.
Any case, I don't want you to confuse with the cosine term. The point is the following, right? Let's do now the subtraction, okay? When you do the subtraction, right, what are you left with is cosine of 2 pi f naught tau, right? Okay. Because this essentially, or minus tau rather, okay? Right? Okay. Plus the subtraction of these other two terms, right? Which is, will be k by 2 t minus tau square minus t square, right? Okay. Again, you can have this 2 pi, okay? So this will give you t square will be cancelled, right? This will lead with you 2t tau, right? And we can drop the tau square term again, okay? Right? So that will, this 2t tau, right, will cancel by this 2, right? Okay. And essentially you will have 2 pi kt tau, right? Plus minus 2 pi f naught tau, okay? So, sorry, my bad, okay? There are two terms, right? This term is a high frequency term, okay? Right? Everyone with me on this? Sorry, let me take a step back here, okay? By the way, today's class is just to show you still there is a lot to learn, okay? Right? And you haven't learned enough, right? But you can still learn more, okay? So this is essentially a high frequency term, right? Everyone follows this? Keshav?
Yeah, I'm following you.
This is high frequency term, right? Okay. This is the only term which has low frequency, okay? So what you do is once you get this signal, right? Okay. you essentially pass it through a low pass or a band pass filter. Okay, this covers your epsilon, right? Okay, and it blocks those 4f0 components here. Okay, right? So you do a band pass filter here with epsilon as the blocker. Okay, everyone clear? So to summarize, okay, now what you will be left with, okay, I'm going to take today a few minutes extra just so that we complete some more concept, right? Okay, so you'll be left this cosine of 2 pi f naught tau, right? And cosine of 2 pi k tau t. Okay, this one will lead to cosine of minus 2 pi f naught tau plus cosine of 2 pi k t tau, right? Okay, essentially instead of exponent, now you have a cosine. Okay, right? Does it make sense, folks? Now this signal, then your y of t multiplied by xt, right? Okay, gets through a high pass or band pass filter, right, where it blocks that 4f0 term, and then it goes through ADC, right? And this ADC, let's say, if it still also is a real ADC, right? Okay, what it means is that you get cosine of minus 2 pi f0 tau plus 2 pi k t. Instead of t, it will become nts tau. Okay, right? Now you take this FFT of this, right? For example, right? Okay, what do you expect to see first of all? Somebody want to guess this thing? You will see two spikes, one for k tau and one for minus k tau, by the way. Okay, just because this is cosine. Okay, all right, everyone clear on this? Keshav, Eric?
Yeah.
Yeah.
Okay, so in matter of, let's say, last 20 minutes, right? Okay, what I have showed you, right, is probably super interesting, right? But at the same time, super complex, right? But there are some tricks you can do here, right? Where ADC can be sampling at 2 NTS and then you can make this complex and so on and so forth. Okay. All right. And I think, and then it will break down the representation to what you have been working and studying with. Okay. Now, this goes back to me to take to your question, right? Okay. What happens when you have an open loop VCO? The problem with the open loop VCO is that, okay, will you get range accurately? Okay, you will get range accurately, guys. Okay, what will be problem here, right, will be that the f0 here, right, which you have for f0 tau in the first chirp, right, will change to the f0 plus delta in the next chirp. Okay, everyone with me on this? Now, what is the problem with this? Tell me. It breaks the fundamental bone. Okay, because everything after this, right, you did, right, the Doppler, the angle of arrival, everything was dependent upon that f0 tau term. Okay, all right, everybody following me here? Sorry, my video is turned off. Oh, okay.
Yeah, you turned it off for to give you bandwidth for the screen.
That I did, but I probably should have turned it back on. Okay, any case, all right, Eric, you guys are following me? Puneet, Helena, making sense?
Yeah.
How nasty can the real world be? Okay, all right, so let me
Yeah.
propose the final point to this, right? Okay, the final point to this, and this is nothing to do with waveform design, is that you have VCOs, okay, which essentially are fed with a very accurate low frequency chirp, right? Okay, and they have a closed loop PLLs, okay, right? Okay, again, don't ask me these things. Okay, how does it work, right? Okay, this is feedback. Okay, right, and it essentially keeps adjusting this and tries to match to this external input. Okay, right, and this tries to make that your VCOs generated are not changing these frequencies, not changing the slope, right? None of those variations are taking place. Okay, right, so this is how people design, let's say, FMCWs, okay, which are stable. Okay, right, And if they are unstable, right, it breaks the fundamental paradigm of doing delays, Dopplers, well, not delays, but Dopplers, and then angle of arrivals and so on and so forth. Okay, right? So that's number one, right? Now going forward, right? Okay. Now FMCW is not the only waveform which is out there, right? Okay. Now just to recap, why FMCW? Okay. Anyone want to say why FMCW? Keshav? What is the alternate to FMCW?
When you send out the chirps one after the other, like
No, that's still FMCW, right? It's frequency modulated carrier wave, right? FMCW is any signal which has this triangular behavior, right? Okay. With frequency and
I
time.
meant the pulses. So like you have the pulses of
Yes,
increasing.
ultra wideband, right?
Right.
Okay. Where you essentially send these pulses out, right? Okay. And then pulses, right? Okay. Instead of chirp. Okay. So that's another way of designing it, right? But what is the fundamental property we need to meet for a waveform to be usable for a radar? So the interference needs to be suppressed, okay? So any waveform, right, okay, which has very good high autocorrelation function, right, okay, will tend to essentially create an effect, right, where it will separate out the interference, which is the leakage path, right, okay, and will leave all the signals, right, okay, which are non-leakage based, right, or non-leaky, right, which are farther away in time, right, or farther away in frequency, right, they will get separated out, right, and they will get suppressed, okay, right. So the objective function really is for a waveform to create these autocorrelation and create a way to filter them out, okay, right. So that's really what is required for any good waveform which essentially needs to support radar application, okay. Now all these things, right, which you find are interesting or you want to learn more about it, right, you should probably take the next version of this class to 57B, or enroll more into maybe some other research, right? So that way you can get to learn these real issues. Okay. All right. I'm gonna stop at there, right? And probably take a question or two, right? And let you guys go. Okay. And we had a lot of fun this time around. Okay. We feel really great. This class has got a good structure now, and we'll keep only improving from here. Questions?
Yeah, I have two questions.
Mhm.
The first one is about the free running VCO.
Right.
I'm thinking whether the phase will be an issue there.
Yes, I think in a way, frequency and phase are one and the same if you think about it, Renji. Okay. If your starting phase is off, right? Okay. It's kind of like saying your little bit of starting frequency is wrong. Okay. Right. So in the world of FMCW, phase frequency are like one and the same. Okay. Does that make sense?
Uh, yeah, I mean, okay, I see. Oh, yeah, I see.
Yeah. I will
And
stop recording as well. But yeah, keep continuing. Sorry.
yeah, so